Okay, so good evening to everybody. My name is Nektarios Vlachakis, and on behalf of the section of Astrophysics, Astronomy and Mechanics of the University of Athens, I welcome you on our colloquium. Today we are very happy to have Niccolò Bucciantini as the speaker. A few words about Niccolò. He received his degree in physics from the University of Florence in 2000, and the PhD from the same university in 2004. He has been a postdoctoral researcher and a Hubble Fellow at the University of California at Berkeley, and then an Ordita Fellow in Sweden at the Albanova University in Stockholm. In 2011, he returned to Florence, where he's up to now. He's a permanent researcher at the Osservatorio di Arcetri, and also a joint professor of high energy astrophysics at the University di Firenze. About his work is focused on the study of outflows from compact objects and the interaction with their environment. And he's doing so by solving the equations of the relativistic and when needed, the general relativistic magnetohydrodynamics. In particular, he is an expert of on the development of numerical schemes and their applications to simulations of pulsar winds and pulsar wind nebula, for which he is going to talk us today. And these works, I should say, are important contributions aiming towards understanding the various physical processes in these very interesting, wondrous, as Niccolò called them in the title of the talk, astrophysical laboratories. Niccolò, you can start. Just a note about the questions. You can ask questions at the end of the talk by raising your electronic hand, or you can type in the chat, or even during the talk if something is important, and you can ask even during the talk. Thank you, Niccolò. You can start.
Okay, I thank you all. I thank you, the organizer, for inviting me and Professor Vlachakis. Let me try to share. Okay, I hope all you can see the screen. So I'm gonna carry you through a tour around Pulsar Wind Nebulae and Pulsar winds to show essentially what is the state of the art of our knowledge of this object, and possibly to illustrate the relevance for other fields of astrophysics and especially high energy astrophysics. So the story began in 1934 because it was Baden Zwicky who first formulated the hypothesis that a massive star would die in bright supernova explosion, leaving behind a remnant that collapsed the core in the form of a neutron stars. And we now today know that essentially 8 solar mass is the threshold for star to go to supernovae and to produce neutron stars. And what is left behind from the iron core is an object of about 10 kilometers in size with a mass of about 1.4 solar masses, which is a Chandrasekhar limit for the collapse of the core, and density, which are about a factor a few above nuclear saturation density. So these are beyond what we can reach with the current experiment. And the physics of the interior of neutron star was one of the holy grail of modern nuclear physics. Now, these objects were discovered as a pulsar in 1967 by Jocelyn Bell as a rotating radio transient, actually. And the model to explain their pulsed emission was presented the following year by Gold, is the famous lighthouse model. The key idea is that you have essentially radiations produced by the neutron star through two beams at the poles. And because of the rotation of the neutron star, this beam will maybe point over you and will give rise to the pulse that you actually observe. And in the same year of the discovery, actually before the discovery was published, Pacini suggested that neutron star could be at the origin of the non-thermal radiation, optical radiation at that time, that was observed coming from the Crab Nebula. So he was the first to postulate an interaction between neutron stars and the surrounding environment. So these are the characteristics of normal pulsar. You have a very small object with the typical rotation periods that range from a millisecond to a few seconds. Actually, millisecond pulsars are a recycled object. When they are born in core collapse, typically the initial rotation period is estimated to be of the order of about 1/100 of a second. And the magnetic field is for canonical pulsar of the order of 10 to the 12 Gauss. It can be a bit slower for millisecond pulsar because they have gone through period of mass accretion and magnetic field body. The point is that if you put together a strong magnetic field and rapid rotation, you are going to have a very strong electric field, induction electric field, that drives you the entire phenomenology of these systems. And the simplest model you can build of a pulsar is the so-called unipolar inductor. It is actually a Faraday disk. But the physics that based on this object is the key physics to many high-energy astrophysical sources. So black hole electrodynamics, GRB electrodynamics, magnetar behavior can all be ultimately put in the form of unipolar induction. The physics might be very different in the details, but the key aspects are the same. And the point is that at the end of the day, the electric field that you create in this object is able to extract particles from the surface. Surely electrons, in certain situations, you can even extract ions out of these systems. It's so strong to break the lattice typical ion binding energy and accelerate them to very high Lorentz factor, which in the closed magnetosphere, close to the surface, is of order of 100, but can be much higher as you move outward. Now, what is going on here is that the interior of the neutron star can be thought of as a perfect conductor. You have a very degenerate system, electrons are fully degenerate, so conduction. So any form of resistivity is strongly forbidden by Pauli blocking. And if you try to set a vacuum outside, you will immediately find that the condition at the surface of the conductor is such that you get an electric field parallel to the magnetic field outside of the neutron star. This is an unscreened electric field. And it's so strong that over a distance that you can compute is of order of a few meters actually, or even 100 meters, you can extract particles and accelerate them to such high energy that they will start radiate curvature radiation on the curved magnetic field line. This radiation can interact with the magnetic field itself. You produce pairs through a process of pair production, and you will end up having a pair production cascade. So the most recent model of pair production cascade in the pulsar magnetospheres, the one, for example, by Andrei Timokin, suggests that for each electron that you've managed to extract from the surface, you have of the order of few times 10 to the 5 pairs produced in the closed magnetospheres. So within a few kilometers from the surface of your pulsar. Now, this pair outflow will actually produce a wind. And it is indeed the interaction of this wind with the environment that gives rise to Pulsar Wind Nebula. So the prototypical Pulsar Wind Nebula is the Crab Nebula. And what you're observing is a bubble, is really a wind bubble of relativistic pairs and strong magnetic field. And what you can see here is this filamentary network, the red stuff, is the leftover of the parent supernova explosion. These are the supernova ejecta, are usually helium-rich and neon-rich knots. The whitish bluish stuff that you see is a synchrotron radiation. And it's synchrotron radiation coming from these high energy pairs radiating in the magnetic field. I want to point you that the Crab Nebula was the first source found in the sky where synchrotron radiation was identified, and was identified thanks to the high degree of polarization that's characteristic of synchrotron radiation. The good point of Pulsar Wind Nebulae is that actually they are very good relativistic accelerators and they are closed objects. So you can actually look at their details and you can look at the regions where particles are accelerated. You don't see the pulsar. Unlike, for example, AGN or unlike GRB, which are too far away in order to actually understand the dynamics or the properties of acceleration. Now, the best example that these object accelerate particles that originate from the pulsar comes from looking at the Crab Nebula at different energies. So as you move to high energy radiation, which means you look at high energy particle, you do see that in the Crab there is a shrinkage of the size of the nebula. Now, if you can make a rough estimate, you find that radio particles have a typical synchrotron lifetime that is longer than the age of the nebula. We know the Crab Nebula was born, actually we know the day, the 4th of July in 1054, because we have records of the supernova explosions. X-ray emitting particles instead have typical lifetime, which is of the order of 10, 20, 30 years, depending on what you put in the magnetic field. So ultimately, you wouldn't be able to see X-ray if those particles were not continuously replenished from the pulsar. And more important, you do see X-ray only close to the center. You don't see them filling the outer layer of the systems. While if you look at the radio, you don't see, you see almost an amorphous size, which means radio particles really are volume filling. The other important aspect of a PWN is that they are incredibly efficient non-thermal accelerator. So this is the spectrum of the Crab Nebula, the synchrotron spectrum, going from radio that you see here through optical, soft X-ray, and then there is the hard MEV regions. Now the point is that you can fit this spectrum as a series of broken power. There is no evidence whatsoever in any PWN where you have a good spectral coverage of any Maxwellian distribution. And usually when you accelerate particles in canonical system like supernova shock, the efficiency is quite small. It's 10%, 20%, which means that 90% of your particles end up in a Maxwellian sum. You see absolutely no such things in PWN, which means a very efficient acceleration mechanism. And what you actually see, however, is that the acceleration is quite funny because all the acceleration mechanisms that you usually study in the literature are essentially scale-free mechanisms. They predict a power law for your acceleration. So if you take Fermi, it predicts a power law which is -2. And if it's relativistic, it's -2 point something. But it's essentially scale invariant. What we see in PWN is instead that you cannot fit PWN with a single power law. You usually need at least a broken power. And there are various breaks that can identify the spectrum of Crab Nebula. There is an MEV cutoff, which is related to the acceleration of magnetic field. You can't have synchrotron above 150 MeV, essentially. You have, of course, you have a synchrotron break between particles that are cooled particle and uncooled particle in the nebula. But in many systems, you do require some form of injection break between the radio part and the optical part, which means that there must be something that characterizes acceleration mechanism or break the scale-free properties of standard acceleration. So there have been various mechanisms proposed for accelerating particles. We go from standard Fermi mechanism, however, these usually require very low magnetizations. They require a wind that's almost completely kinetic dominated. You have a magnetic-driven reconnection, which instead works very well in high magnetized wind, but require very high multiplicity, require lots of pairs in the wind. And then you have other mechanisms that invoke the presence of ions. Now, none of these seems to work properly. All of these mechanisms make assumptions that fit very badly. For example, this assumption on the magnetization of the wind doesn't fit very well either with the model of the wind, at the base at least that we have, or with the model of the nebula that I'm going to show you later that require much higher magnetization in order to explain at least the X-ray morphologies. Pulsar multiplicity this high are not recovered in the standard model of polar cap. And on the other hand, if you have this very high multiplicity, you are likely going to dissipate all the magnetic field before the wind reaches the environment, interacts with the environment. For ions, you need a low multiplicity and you need lots of energy deposited into ions. And there is no evidence for this. Also because ions don't emit. The only possible proof of evidence of ions maybe will come from CTA in the future by measuring essentially gamma ray from pion decay. But it's not so obvious if this is going to work because you are really stretching at the limit of current mode. So for example, these are speak simulations of a pair-dominated shock Fermi acceleration. And the result of this simulation is that essentially Fermi works only for subluminal shock. And while in perpendicular relativistic shock, while the one we expect to work in PWN are in conditions that are known as superluminal, and essentially you don't get very strong acceleration, and you have a very pronounced Maxwellian distribution that you don't see in the data. Now, what you can do is hope to use the nebula as an imager for the wind. So we know that these systems are inflated by the pulsar, and the pulsar deposits energy, but it's not just a measure of a calorimeter, which you can do with the global spectrum. You can look at the X-ray and use them to understand how the wind is structured. So we have a model for the wind based on the so-called force-free approximations, and they date back to the 99s, and they have grown in complexity in the recent year, moving through 3D, and now adding even the more recent models include, for example, particle accelerations, some idea of pair productions, and even models that breaks the force-free assumption, introducing some form of resistivity. So this is a 3D model, and it's quite hard to see, but I'm going to plot it. You can see that as the pulsar rotates, you will have essentially winds of opposite polarities forming what's known as a striped wind. So the north and south pole magnetic field line will alternate. Now, this will give rise to wind with certain properties, and especially with the wind with certain characteristic in terms of the equatorial current sheet. So in general, the idea is that you would like to understand how these various aspects of the wind, which are not observable, the wind is cold, turns into the properties of the emission that you will see. For example, one aspect of striped wind is that they can be very good accelerator if you manage to reconnect the wind of different polarities. So these alternating stripes that you see that are produced as the pulsar rotates will at a certain point impact the environment. They will be compressed in the shock at the impact, and this can drive reconnection. And there are models suggesting that these driven reconnection at the shock can produce very hard spectra, the one that you need, for example, to explain the radio particles. So there are various indications that the systems can be quite complex and that you can use the information from this object to infer properties of the wind and of the pulsar magnetosphere that are otherwise unobserved. So the simple model that you can do is to try to model this object as just amorphous ball. So you inject your wind, you choose an injection, some injection prescription, for example. You want to model the properties of the particle that are injected, and then you fit the spectrum, and you try to derive information. And the easiest things to do is to model these things as spherically symmetric object without any internal structure. If you do these things, you can take into account the energy losses of the particle, and you have two terms, adiabatic loss and synchrotron loss, and you end up with a model like this. So the dots are, for example, data from the Crab Nebula, both in the synchrotron part and the inverse Compton, and the solid line is the best fit model. Now, you can really fit very well these systems. Unfortunately, and this kind of approach have been used and is commonly used for objects for which you don't have that many information on the morphology. Unfortunately, things have changed a lot at the beginning of 2000 with the launch of Chandra, because when we begin to observe this object at high energy, this is what we observe. Now, this is, if you look at them, you see everything except an amorphous object. There are structures, and the most important things that you can notice here is the presence of these kinds of ring, which are observed in Vela, in Crab, you can see here, in MSH 1509. You can see this in edge on in 3C58, and of jets. And the jets are weak in some systems like Vela, much more pronounced in other systems. There are other things that you might notice is that the jet tends to have different luminosities, and even these rings are mostly one-sided. And this is usually attributed to Doppler boosting. This is matter that's moving fast at a fraction of the speed of light. So depending if it points toward you or away from you, essentially it's brighter or fainter. Now, all of this must somehow be related to the way particles are injected by the pulsar. So there have been quite deep studies of how to model these structures close to the termination shock. So how to take a model for the wind, plug it inside the supernova, and look what it comes out. So the first things you can do is take one prescription for the wind that comes from, for example, one of these force-free simulation, and use it as an injection properties in an MHD simulation that models the global structure. So what you see here is the very old simulation, one of the first I have done. Essentially, you take a wind which is stronger or more energetic on the equator than on the pole. And this is exactly what you would expect, for example, from the standard aligned rotator. And of course, as a consequence of this wind will slow down in a strong shock, like any wind bubble. But the shock will be much more distant from the pulsar on the equatorial plane, where the wind is stronger, than on the pole, where the wind is weaker. As a result, you will create flow channel in the nebula with speed that are a fraction of the speed of light. And this flow channel, if you compute the typical emissivity on top of this object, will essentially give rise to an emission pattern. And then you can try to match this emission pattern with what you observe and translate these into the properties of the underlying wind. So for example, let's consider a case of a striped wind. So this is your wind model. You have the pulsar here. Pulsar has a magnetic axis which is not aligned with the rotation axis. As a consequence, in the wind, there is a region known as striped wind region, where the magnetic field of the wind alternate polarities. And you have polarity that alternates every half rotation period, which means that the distance between this stripe and this stripe is of the order of the light cylinder of the pulsar. Let's say about 500 kilometers, 1,000 kilometers. Now, when these stripes reaches the nebula, which is about the size of about 1 parsec, you can imagine that they get compressed and they annihilate completely. So ultimately, it will look like in the equator there is no magnetic field. There's an annihilation of magnetic field. Now, if you take this model for the wind, and you, with an annihilated magnetic field in the equatorial region, you plug it inside the simulation of the environment, you get a flow structure that looks like this. And I'm going to illustrate. What you see here in red is the region occupied by the pulsar wind, the ultra-relativistic pulsar wind. And the wind pushes on the equator much more than it pushes on the pole. Now, what you have is you have unmagnetized channel in the equator, and so matter on the equator flies outward toward the edge of your supernova remnant, where it will impact the supernova remnant somewhere at a larger distance. But there is matter where the magnetic field is not annihilated at intermediate latitude. And what happens is that there will be up stresses, magnetic field stresses acting in the nebula that will essentially recollimate the matter. And this will give rise to a jet. So even if you have no jet at all in these systems, even if this system is mostly equatorial, the end is that in your nebula, there will be matter flowing into a relativistic jet. Now, this is a plot of the velocity structure in the PWN, but you don't see velocity. You see synchrotron emission. So what you can do, you can take a prescription from for acceleration on the shock. Now you get and follow particles, accelerated particle as they move into the nebula. Now each accelerated particle will lose energy as it moves into the nebula, it will radiate. And then you can compute the contribution of each of these particles to the radiation seen by an observer, which will depend on the inclination of the systems and on the frequency at which it is observed. Now, if you do all of this, you end up with something like, you will end up with something like these systems here, and you don't see very well. So essentially, this is a map of the system, and this is an image from HST of the inner region of the Crab Nebula. So what you see here is that basically each of these features is based on a simulation, map to one of the observed features. They don't map exactly one-to-one, but you have, for example, this bright feature here, which correspond to the so-called knot in the Crab Nebula. You have these that correspond to the outer torus, this region here that correspond to the wisp region that sits here. You have this thin ring here that correspond to this ring here. And the interesting point is that now that you have a simulation, you can actually ask where each of these emission features come from. So now you have really a proxy that allows you to relate each one of the features that you observe to a specific position in the nebula. And you can identify them, the knot and the ring and the torus, with a particular position close to the shock or along the shock or close to the equator. So if you have a model for acceleration that, for example, is latitude dependent, then you would expect different properties in the knot than you have in the torus, because they come from different regions of the nebula. And you can toy with these systems because your simulation allows to switch on and off each of them to use a different acceleration prescription and see how things changes. So just to show you what we have been able to do, so this is a Chandra blow up of the Crab Nebula, and this is one of the best axisymmetric simulation we have been able to do by tuning the parameters. So what we see is that we are able essentially to recover almost all the structure that we see with the relevant positions and to a certain extent also the relevant intensities that we see in these systems. And I will return on this in a minute. And at this point, you can really map one-to-one these features and you can do data analysis. Now, all is not that good, I mean, okay, because it's true that this is an image, but now you can work on the details. So if you look at the details, there are a few problems with current simulation, with the, let's say, old state simulation. And one of the biggest problems is that all this simulation assumes that the magnetic field in the pulsar is, let's say, fully ordered. It's a very strong and very ordered magnetic field. There is no turbulence, if you want, in these movements. So they work very well in explaining the X-ray, at least in the internal region, but they have some key flaw that we haven't been able to solve remaining in this regime. So just to show you a few of these issues, one of the main problems is that we reproduce the spectrum of these systems, the integrated full spectrum of these systems. So these models are very good if you want to reproduce the X-ray, but if you try to plug in and reproduce all the way from radio to X-ray to TV, you encounter lots of issues. Essentially, you need to add the population and to fine-tune everything, and they're not working that good. This is in contrast with the models that assumes that everything is just an amorphous ball that fits systems very well. And if you think of it, systems that assumes an amorphous ball ultimately are like mixing everything up. While MHD systems that assumes very ordered structure essentially are mixing nothing. So there must be something that goes on in between these two. The other issue that we have is that 2D models, the ones that are laminar one, fail to reproduce the torus brightness of the Crab Nebula. So in general, if you look at this very ordered model, the torus is fainter than the wisp. And remember this point, because I will come on this point later on to show that this may be an indication that turbulence is a key properties of this system. So in the recent years, there have been an effort to model this system into 3D. And this is a 3D simulation showing the structure of the magnetic field. You can see there is some mixing. Now, the problem with 3D is that these are enormous simulations and are very hard to run for the simple reason that you need to model an object which is 1,000 years old. And the time scale that you need to resolve are week-long time scale because the injection varies on time scale of weeks. So ultimately, it's not possible to do so. So the longest 3D simulation runs for about 100 years. So we have to, there are lots of work gone into properly rescaling this object when you want to compute emission. Because if you want to compute emissions, you have to compute the emission with respect to a 1,000 years old object, and you cannot just advect particle for 20 years and hope that will give you the correct synchrotron cooling, for example. You have to rescale everything. The good point of 3D simulation is that they show that the internal region of these systems doesn't have that much turbulence. So they recover the jet and torus structure that we had in earlier 2D simulations. And the other issue that we have with these is that usually they require very high magnetization. So the wind must be very strongly magnetized in order to produce the structure that we see. Again, not all is good and solved with 3D problems. So we know that 3D managed to reproduce quite well the internal structure of the Pulsar Wind Nebula, the structure close to the termination shock, but they fail to reproduce the emission properties in radio. And this is unfortunately a common problem of all these systems. So this is a radio map based on a 3D model, and it doesn't look like anything in radio we see in the Crab Nebula. And the main reason for this is that essentially all that you see in this map is Doppler boosting. So it's based on how essentially matter moves toward you or away from you. There is a volumetric effect. So say radio particles are feeling more, but there's also a magnetic field that weights the central region where it's stronger more than the sides. The problem is that the strength of the magnetic field and Doppler boosting are all achromatic. So if magnetic field is stronger, synchrotron emission will be stronger in X-ray as well as in radio. If the Doppler boosting enhances emission, it will enhance in X-ray as much as in radio. And the point is that it's very hard to have something, an MHD process that selects radio versus X-ray. So this is the main issue that we have in fitting this model. The other issue is that all these models give a very small magnetic field. They tend to under-predict the magnetic field by a factor 2, which creates issue in reproducing, for example, the inverse Compton emission. So an idea is that perhaps there is something missing, and the idea that something missing goes back to essentially the presence of turbulence in these systems. But before addressing turbulence, I want to show you essentially where these all originated, and it originated from time variability. So these objects show time variability. This is a movie of the Crab Nebula. You do see there is these kinds of waves that seems to originate from the inner ring where the shock is located and move outwards. Now these are very well seen in the Crab. The variability have a typical time scale of about a couple of years. There seems to be a duty cycle going on in these systems. I want to remember that the pulsar is rotating 33 times per second. So this variability has nothing to do, it's completely unrelated to anything that can happen in the pulsar magnetospheres. So it must be something that has to do either with the shock or with the nebula, because the timescales are of the order of the light crossing time of these regions. Variability is also seen in, for example, B1509 is seen in Vela. I would say variability is seen in any object which is bright enough to have enough counts to actually make difference map between one epoch and the other. Now, what is the origin of this variability is not very clear, but what is been seen in numerical simulation is that variability naturally arises because of the properties of the wind. So here you have a pulsar that sits here, that's producing a wind, and this is a cut in the nebula showing the shock. What you see in red is kind of pseudo entropy. You can imagine it as a characteristic energy of particles that are accelerated. Now, of course, the wind is stronger on the equator, so the shock would be at larger distance on the equator than on the pole. The blue stuff is the PWN, Pulsar Wind Nebula. Now, if I turn the wind on, this is what happens. The wind is a steady state wind. There's absolutely no variability in the wind. What's happening here is that, what's happening here is that given that this shock is highly oblique and there are flow channels that moves at very high speed in the nebula, there are lots of vorticity. Now, vorticity drives sound waves. The sound waves moves along the shock and it drives instability. So this is what is known as a steady accretion shock instability. It's well known in the supernova community where it works the other way around. You have an accretion shock. Matter comes from outside toward the inside. It shocks. It drives vorticity, and this vorticity creates an instability of the shock. Here you have the same properties seen the other way around. You have a material coming from the interior, going through a shock, creating vorticity, and this vorticity perturbs the shock. Now, you can then do this. You can redo what we have done. So take this, inject particle with your injection prescription, advect in the nebula, time-dependent advection, compute their synchrotron emissivity, and see what it looks like. And if you do this, you find, for example, that you find this is a variability of the emission in the inner region of a PWN computed on a simulation, on an MHD simulation. So you run your MHD simulation, you take the integrated emission from the central region, you compute the variability, and you will see that there is fluctuations, of course, because sometimes matter is pointing toward you, sometimes it's pointing away from you. And you can do an FFT, a fast Fourier transform of a wavelet analysis of this variability, and you find there is variability on time scale of the order of a couple of years. This time scale is also seen in high energy emission from PWN. These are RXT and Swift and GBM, so MEV emission or hundreds of keV emission, seen from the Crab Nebula. And you do see that there are fluctuations in the intensity over periods of about a couple of years. So luminosity is going up and down by a few percent, of course, because this is just sampling a small region. But the most striking things of these systems came just around 2011, 2010, when in the Crab Nebula, it was observed the first flare. This is a gamma ray flare. So in a matter of a couple of days, the gamma ray luminosity at around 150 MeV of the Crab Nebula went up by a factor 11. And it was making this object one of the brightest gamma ray sources in this regime for that week. So the point is that this was completely unexpected. You have to think that the Crab Nebula was thought to be a calibrator for gamma ray instrument. And now we know that it is not. There are flares that can be very bright one. This was incredibly bright, but there are continuous fluctuations of about a factor 2 going on in the MEV emission from this object. What was incredible of this flare was that essentially it was basically a monochromatic event. It was seen in gamma ray and just in gamma ray. People looked at the pulsar, radio emission, and there was absolutely nothing in the timing residual of the pulsar. The pulsar wasn't doing anything. It was spinning down in a very regular way. People went looking at the X-ray emission from the PWN to see if there was something changing in the X-ray, and the X-ray map were exactly what you were expecting in the quiet system. So essentially it was like there was a burst of particle injected at 100 MeV and just shining in that energy range and nothing else. So it's really, so it was an impulsive event, an impulsive energy injection event. And the best model that's today advocated to explain this system is, let's say, an episodic reconnection event. Somehow you created a very strong magnetic field, a very strong current shield. You had a very fast reconnection event taking place in a matter of weeks because these things went up and down over 2 weeks. So particle acceleration was very fast. And you can essentially use all the potential energy of your reconnection site to accelerate particles. Now, of course, you do need to have lots of current sheets. And likely reconnection is going on all over. It's only those very episodic events that you are seeing as flare. So this draws the attention toward the fact that there might be lots of turbulence going on in these systems and lots of mixing. And these put back some of the ideas that were presented in the past. So there was a suggestion in the past that turbulence could be important. And they were based on essentially the variation of the spectral index in these systems. So what I told you in one of the first slides was that if you look at lower and lower energy, you see a larger and larger nebula. And I told you that this was exactly what you were expecting for particle injected at the center and then moving outward. The problem is that the high energy particles fill a region that is too large. So if you take any model and you try to now not just do the qualitative way, but to put numbers on how large should be the X-ray size versus the optical size, they don't work. Essentially, you need to diffuse the high energy particle more than what simple laminar model would predict. And you need to diffuse them more than what bomb diffusion will actually predict. So in a certain way, there must be something that mixes particle in the nebula, or manage to bring particle from the inner region toward the edge of the nebula much faster than what the flow would do. Now, one way of doing this is driving turbulence. So having lots of turbulence in the nebula. There is a problem, however, that's very hard to look at turbulence. You can imagine that we have the same problems for hydrodynamics turbulence. I mean, when you drive your car, you create lots of turbulence behind you, but those that are driving behind you don't see the turbulence. Yeah, you need very clever experiment with laser beam in order to see phase difference and sample a turbulence field. So how are we going to model turbulence in an object where we can't really stick a probe inside and look at the velocity field? And one way to do this is through polarization. Now, polarization tells you is a measure of how ordered the magnetic field is. So if you have a magnetic field which is all in one direction, you will get completely polarized synchrotron emission. But now, imagine you have magnetic field different patches with different orientations. This will essentially not affect the emissivity. The synchrotron emission will be the same. But when you compute the polarization, given that you have different polarization coming from different regions, ultimately you will depolarize your emission. So measuring the polarized intensity of this object is an indicator of how much energy is in turbulent magnetic field. Now, what we know about the magnetic field of this object is this. There are a few systems, I'm showing just two, Vela and G106, where the magnetic field is very, very well ordered, very well structured, high degree of polarization. Everything you would expect from a laminar model fits perfectly with this polarization. And then you have systems where nothing works. If you look at the polarization pattern, it's exactly the other way around what you would expect. Unfortunately, what we have is that we can only measure polarization in radio. And that's the problem. Radio particles are volume-filling particles. They're old particles. They suffer from the interaction with the supernova remnant. So they're really telling you nothing of things happening in the injection region. You would like to see high energy particle polarization. The only place where these have been done up to now is the Crab Nebula. So this is an image of the Crab Nebula. You can see here is unpolarized radiation, and this is polarized intensity. And if you look carefully, you will see that in polarized intensity, the torus is much fainter than the wisp. This is exactly what the simulation, the laminar simulation with no turbulence at all, will predict. When you look at unpolarized radiation, the torus is much brighter than the wisp, which means that there is a lot of turbulent magnetic field that contributing emission, but not polarization. And by comparing the fraction of polarized versus unpolarized radiation, you can estimate the amount of turbulent magnetic field that you have. Now, optical is tricky because unfortunately, you can only do this measure in the Crab Nebula. All other objects are too faint. Some of them have not even an optical emission observable. And there are lots of issues with foreground and contaminations that makes the things a mess. So in general, for example, you see another region which is quite interesting is the base of the jet. The base of the jet is completely unpolarized, but it's very strong in emission, which means that there is lots of reconnection and turbulence going on in this place. This is a highly dynamical region, and many people have invoked gamma ray flare originating from this region here. So we have even detailed measure of polarization in each of these features. These are the WISP, this is the zoom out, taken with HST. And we do see, for example, that moving away from the pulsar, taking the knot, which is this bright feature here, and then the WISP, you see that the polarization degree just goes down, which means that there is an increasing level of turbulence moving in the nebula, and emission regions which are associated to the shock have a high level of polarization, which means the shock has a pretty strong and structured and ordered magnetic field. Now, you can try to plug in turbulence in the model. And we have been done this recently. So adding turbulence to a laminar model and see what happens. So there are recipes with which you can include turbulence as a subgrid effect, model polarization, and model diffusion. And if you do this, now you can get map that can reproduce the correct intensity of the torus and can match very well what we observe in emission. And you can use this as a proxy to infer the amount of turbulent energy. And we found that in general, in Pulsar Wind Nebulae, turbulent energy is about, let's say, about 30 to 50% of the ordered magnetic field energy. So you need to have a delta B over B of order, let's say, almost unity. And the reason for this is that essentially when you look at the polarizations, only the turbulent component perpendicular to you matters. So you have three turbulent components of the magnetic field. The one pointing toward you doesn't matter because it doesn't contribute to synchrotron emission. The one aligned with the ordered magnetic field doesn't matter because it doesn't depolarize, and only one of the components really matters. So there are you need lots of energy in order to get even a weak depolarization effect. Now, you would like to test these things also in other systems. And the problem is that it's really, really hard to do that because other systems are less well constrained than Crab. And I'm going to show you, for example, the kind of ambiguity you run when you try to model these systems. This is an image of MSH 1552, where you see this is a jet-dominated system. You have the ring and the jet. And these are three models of the same object done with three very different prescriptions for the magnetic field in the jet. This is just intensity. So there's no way that just by looking at the intensity map, I can guess what is the structure of the magnetic field in the jet. I can do this in Crab, where I have a very high, an enormous number of counts, very good handling on the spectrum, very good signal to noise. But in other systems, that's not possible. And perhaps we will be able to do this next year when we will launch this. This is the Imaging X-ray Polarimeter Explorer. So this is aimed at detecting X-ray polarization through imaging, so resolving these PWN. The point is that we have the only object where we have X-ray polarization measured is the Crab Nebula, because it's a very bright in X-ray. But these are only integrated observations and usually taken through airborne balloon or things like that. So it's just one point. We don't have really a space resolved measure. So we cannot say if polarization changes in the nebula or how much is in the torus. So this is a standard X-ray telescope, is 3 modules. Each module is a multiple shell mirror. And globally is about 700 square centimeter collecting area. So it's quite good. It has a 25 arc-second resolution. So it's not as good as Chandra, you can't do that, but it's enough to actually resolve some of the main features in a few selected PWN. So this is the list of the PWN that are supposed to be observed, and essentially this is the observational times in days and the expected polarized fraction that we will hope to observe. The technique is based on a gas pixel detector, so essentially you have your incoming photons, will create K-shell electrons that will jump out of the atoms, and by following the track of the electrons, you will reconstruct the polarization, the direction of the electric field of the incoming photons. And this is the modulation curves, which show you that the performance are quite good in the range 2 to 8 kV. So the other good point of this telescope is that it's going to observe exactly on the same band where Chandra is observing. All the other airborne balloon experiments usually work at 100 kV, so way above this regime. So now you can actually look at the Chandra map and identify on the Chandra map the region that you are interested in. So this is a simulation of what we hope to observe in the Crab Nebula. Essentially, an object like the Crab is going to be able to resolve over about 9 regions, something like that, which will be more than enough to cover the torus and the jet. So we'll be able to see if there are changes of polarization in the torus versus the jet. We'll not be able to see the small structure in the inner ring. One of the best objects where we are going to see things is MSH1552. This is a Chandra map, and we have superimposed on the Chandra map the result of a polarization model. So we are going to be able to tell how the polarization is in the disk region and all along the jet. So this will be able for the first time to model these kinds of sources and tell us information on the structure of the magnetic field. Now, before I finish, I want to discuss one other aspect of this object, which has become quite interesting in the recent year, is that much of the work that has been done in the past have focused on young systems. The Crab Nebula, Vela, MSH1552, G21.5. These are very young objects, where you have the pulsar, you know how things work. This is the supernova remnants, the Pulsar Wind Nebula sits inside. You can build beautiful models, everything is stationary. Point is that there are plenty of very old objects in the sky. And with the upcoming CTA observatory, we are going to see plenty of them. Actually, the galactic background is going to be dominated by old PWN. So understanding how old the PWN system works is going to be pivotal for next generation gamma ray observatory. And unfortunately, old PWN are a mess. Because the interaction with the supernova remnant, the movement of the pulsar, proper motion of the pulsar, everything is going to make your system very complicated on one hand. On the other, we know very little of these systems. In the Crab Nebula, we know almost everything. The age of the pulsar, the spin down history, we can model the mass. It has been observed with every instrument that has ever been built. So we have incredible spectral coverage. For many of these systems, we have a very poor spectral coverage. We only see a few bands. We don't know the age of the pulsar. Sometimes we don't see even the pulsar. So it's very hard to make the tailored model of these systems, but we need to start building at least or sampling the parameter space. So this is what happened when a PWN, the black stuff here, the low density stuff, interact with the supernova remnant. And you see that there are lots of turbulence getting driven and lots of mixing. We do see systems where this happens. This is one old system where you have the pulsar that's here. This is a relic PWN observed in radio. This is about 11,000 years old, these systems. And this is a map of the polarization. And all of this polarized emission essentially is due to the mixing of the supernova remnant with the pulsar we have. Now, when this pulsar will die or will be lost, we will still be able to see these electrons. And this will be seen not just as a radio emitting electron, but as inverse Compton TeV emitting electron. So they're going to produce lots of TeV emission. And we see plenty of these objects. These are two S sources where we have a pulsar. We believe the pulsar is associated with the S sources, but there is absolutely no evidence. I mean, it's just a coincidence. They are sitting in the same position. And what we think we are seeing is actually the relic electron injected over 20 to 30,000 years by this pulsar and creating a bubble. And we have no other observation of these systems, for example, in radio and X-ray. So there are plenty of these systems like this. Now, one systems that we know associated with old pulsar are bow-shock PWN. So the pulsar escapes the supernova remnant, moves through the ISM, and begins to interact with the ISM. And it will create a system like a cometary system. And we will see here a couple of them. They were originally discovered as H-alpha nebulae. You have a pulsar here moving in this direction. And H-alpha nebulae, because the ISM contains neutral hydrogen, the neutral hydrogen goes through a shock, gets excited, and produces H-alpha. But there are only a few of them seen as H-alpha nebulae. Now, there were just few objects, so there wasn't much interest in this system until, let's say, a few years ago. And much of the interest in these systems was driven by the so-called antimatter excess observed in the Pamela experiment. Pamela is one of the detectors on the AMS station and measures essentially cosmic rays. And what they found is that in the cosmic ray as measured by Pamela, there was an excess of positrons. There were far more positrons than what you could explain with a simple secondary mechanism with standard cosmic ray. So an issue is, what is the origin of these positrons? And if you go through the literature on archive and you search of it, you will find thousands of papers that explain the positron as signature of dark matter. So the positron excess of Pamela is thought to be one of the most promising signatures for the presence of dark matter that we have at the moment. Unfortunately, pulsars are very excellent machine at making positrons. You remember what I say in the first slide, out of each electron you extract from the surface, you made about 10 to the 5 positrons. And they must go somewhere. And the point is that, well, as long as the Pulsar Wind Nebula is inside the supernova remnant, they will sit there. But as soon as the PWN goes out, if the pulsar is still active, there will be positron injected throughout the ISM. And once they're injected throughout the ISM, they will not lose because the magnetic field in the ISM is virtually negligible. And you can fill the galaxy with positron just produced by pulsar. So ultimately, this might not be your smoking gun for dark matter, but just a standard astrophysical source producing a lot of antimatter. So this means that you have to understand how the dynamics of the wind interaction works in these systems. And the nice point is that you have plenty of bow shock observed today, not just in H-alpha, but in X-ray. Because what you see is that the wind injected by the pulsar will give rise to accelerate particle, this will emit X-ray, and you will see this long X-ray tail. Now, unfortunately, it all looks nice and good in simulations and in the many PWN that you observe, but there are a few, what I call the bad boys, okay? So bad boys are objects that don't behave the way you would like them to behave. And here's an example of the bad boys. The first bad boy is probably the guitar net. You have a pulsar here, the pulsar is moving in this direction, and you know that there is an H-alpha shock in this direction. So every model you can build of, MHD model, it doesn't matter, will tell you that your wind particle, your pulsar wind particle should go in this direction, should be left behind. Okay? A comet has a tail, and the tail sits behind the comet, not ahead of it. What we see in this system is that there is X-ray emission in these fissures. It's 90 degrees from the pulsar direction. It's outside the shock with the ambient medium. If I go back to this slide, you have wind particle from the pulsar going in this direction. There's nothing in this direction. As ISM, everything is going backward. It's pushed backward by the movement. And you do see similar things in other PWN. On top of which it is only one-sided. You see particle only on this side, you see nothing on this other. This is another object where you see particle ahead. So somehow particle managed to go out of the pulsar, but instead of being confined by the surrounding medium, they escape ahead of the shock. And finally, another things that have been noticed recently are these TV halos. So the first one was detected close to Geminga, which is here. And Geminga is a bow shock PWN. We do see a beautiful bow shock in X-ray. When you look at X-ray, there is no evidence whatsoever of anything escaping from the pulsar. When you look at TV, you see lots of electrons outside. Where they do come from, they must somehow manage to emerge from the systems and contaminate the ISM. So we have gone through modeling of these systems, doing much better 3D models with respect to what have been done in the past. And this is an example of a 3D model of a bow shock PWN. I understand it's quite complex. You have a pulsar sitting here. You have your wind region. The wind is stronger on the equator, is 45 inclined. There is ISM coming from this direction. And what you get is that a wind cavity and lots of mix. You can look at the velocity structure. You will see this high velocity channel. But the most important things you can look at is the magnetic field. And you do see, if you look at the magnetic field, there is lots of mixing and magnetic field turbulence. So we have done a complete sampling of all possible configuration in terms of pulsar orientation, strength of the wind, strength of the magnetic field, asymmetry of the wind, structure of the magnetic field in the ISM. We have run some, probably more of 100 simulations on 3D of this object. And we have a complete set of different cases. The wind could be isotropic or anisotropic, strongly magnetized, weakly magnetized. You see, for example, that in strongly magnetized systems, turbulence is completely suppressed. And you do see that, show you, this is a difference between you see in the magnetic field in a weakly magnetized nebula and in a strongly magnetized nebula, where you see the current sheet as well preserved. Here, everything is mixed up. What we have been done is look at what happened to particles in these systems, because this is an MHD model. So it's a fluid model, and by default, particles are frozen to the field lines, to the magnetic field lines. But this is true for low energy particles. High energy particles will not be frozen. They gyrate in the system. So what you can do, you can take one of these models, and I have one here, and add particle on top of this. So I'm going to show you what we are showing here. This is magnetic field. You have a pulsar here. You have an equatorial current sheet, and you see this equatorial current sheet in the wind survive in the nebula because it's strongly magnetized. You have a polar current, and the polar current impact the ambient medium, and it's diverted in this way. So what happened here is a strange thing. It's very similar to what happened in the wind. The pulsar wind has two opposite polarity in the northern and southern hemisphere. The ISM magnetic field has a single polarity. So in one hemisphere, you will have a wind and the pulsar will interact with different polarities and will create a current sheet. On the other hemisphere, you will have that the pulsar wind and the ISM have the same polarity and will create a magnetic wall. And these two structures have a very different properties for particle confinement. So now you take particle, you inject them, and this is what happens if you inject particle in the polar region. So here is a zoom, polar current. The polar current goes in this direction. You see that here you have a current sheet. Here you have turbulence, so you have a reconnection site. Here you have a magnetic wall. You inject particle. The particle, of course, magnetic wall stop them. They move along, they are confined by the current sheet until they reach the reconnection site. Once they reach the reconnection site, they start to jump on field line that connect with the ISM. And I'm going to show you what happened here. So what happened is that you look at the particle. This is a cut of the system from behind, and the particle escape outward of the system. So you see lots of particles that goes out. These are particles of different charges will escape in different way because your current sheet behave differently for different charges. You have charge separation. And at the end of the day, out of this system, you plug particle on top and you get this. You get outflow of particle in the ISM. So essentially, particles that should be confined within these systems, because of reconnection going on at this interface and turbulence, manage to stream out. Now, in this simulation, you get these two streams are exactly symmetric. But this is because of the geometry they have selected. I can select geometries where I get asymmetric outflow. And this is an example, okay? These are particles of different energies in a very complicated pattern in terms of inclination. But what I want to show here is that you have different escaping regime. Very high energy particles essentially diffuse outward. And as you can see, there is some difference between the two charges, but the process is almost uniform. But as you move to lower energy, you find that particles tend to diffuse more on one side, escape more on one side than in this other. So this will explain why many of these features are just one side. The other interesting aspect is that you don't have the same number of positive and negative charges that escape. So the escape is charge separated. And this is quite important because in order to explain the TeV halos that you see in Geminka, you need a high level of local turbulence, much higher than standard ISM turbulence measured by pulsar scintillations or any other technique. So there must be something locally that enhances turbulence. And the idea is that, well, it could be the cosmic ray themselves that enhance turbulence through some streaming instability. But in order for streaming instability to work, you need the net current. So you need the charge separated flow, because charge neutral flow drives, essentially can drive non-resonant instability, and non-resonant instability are tendentially very weak. They are not very efficient at enhancing the turbulence. So the fact that because of reconnection and because of the existence of these magnetic layers, you can have particle separated outflow, can help you drive more turbulence in the surrounding environment and explain all of these features. Let's go back to the first slide that I have, this one, to show you the Guitar Nebula. So this feature has a length. It's about a few parsec long. If particles were injected and there was no turbulence, you would not be able to see these features, because particles will have just streamed hundreds of parsecs away. So particle, it's true that particle managed to escape, but somehow they managed to get stuck here and produce emission. And in order to get stuck here, you need to have a delta B over B of order 1 in this feature. So a strong magnetic turbulence. This is not what you would expect on this scale if you take the standard turbulence of the ISM. So all of these features require some form of self-amplifications, so which is consistent with the idea that they are charge separated. There's a certain level of charge separation. So ultimately, understanding how this old object behaves is quite pivotal to understand not just the gamma ray emission background that you're going to see plenty of these halos, but also to understand non-thermal particle and antimatter in the galaxies. And remember that there are places like the galactic center where you're going to have plenty of pulsars. And if they're going to contribute lots of positrons, all the annihilation line that you might see from the galactic center, for example, could just be pulsar origins and have absolutely nothing to do with dark matter. So this is one of the key features that people are trying to understand today, how much this particle can escape, if they can really reach Earth, and if the position that we see at Earth can really be contaminated by these things. And I'm going to conclude here, because I think I'm at the end of time, just by saying that essentially these systems allow you to, well, let me put it this way. If you try to model just one aspect of these systems, old systems, young systems, accelerations, the dynamics, the emission, the pulsar, you might build a good model of it. But now the problem is putting all of this together and building a unified model, because ultimately these are global machines. The pulsar drives an outflow, the outflow drives the nebula, the properties of the nebula and the acceleration, all of them must be tied together. And the major issue that we have today is try to take all of these ingredients from different physics and computed in different way and in different regime, and put them together to see the constant, the global constant that we can get. How much emission can rule out acceleration mechanism, how much pulsar magnetospheric model rule out MHD model for the PWN, how much particle diffusion rules out, for example, MHD models for all the objects. And essentially, this is what we are trying to do now, which is the hardest things to do, actually, putting together. And I'm thanking you. If you have any questions, please.
Thank you, Niccolò, for the nice talk. Okay, questions?
Thank you very much.
Thank you.
I don't see hands.
Yes, I don't
Okay,
see.
maybe I have one.
Okay.
Okay, Apostole.
Okay, so thank you very much for your talk. Actually, I was in Florence many, many years ago when Rino was a young postdoc.
Ah.
And I also met Franco, who was doing, of course, all this work on the Pulsar Wind Nebula, very, very innovative and pioneering by the time. Thank you very much. It was a very interesting talk. But I have one question. It was, you showed all these amazing maps, and then you showed also spectra. So somehow you put particles in what way on these amazing maps? This is something that I couldn't understand.
So
it was accelerated, or they were put in somehow by hand?
Okay, there are various degrees on which you can do things by hand, let's say.
Yeah.
So the simplest things you can do is essentially you inject them at the shock. So you select the prescription for your particle at the shock. For example, you assume that at the shock you accelerate a broken power. and it can be different in different position of the shock. Then you follow fluid particle as they move in the nebula through these MHD simulations. There are various techniques that you can use, Lagrangian particle or MHD tracer. And from that, you derive the in each position of the nebula, you derive the local particle distribution function. So the simplest things to do is that you model two features of the spectrum. One is the injection break, and the other is the cooling break. So this is the simplest things you can do. So in each position of the nebula, you will have your cooling break and synchrotron break. You reconstruct the particle distribution function, and you model the emission. And we are now trying to do this in a more complex way, adding real particle in the sensor object, which carry a particle distribution function, because we want to account for mixing, because there are lots of problems handled strong turbulence and mixing. We don't do acceleration at the shock because the scale, in order to model acceleration, are usually the peak scale that cannot be resolved in MHD. But what you can do, you can take the prescription from peak and associate it with each position on the shock. And we have tried to do this in order to model, for example, the difference between the optical wisp and the radio wisp. Optical wisp and radio wisp are not exactly the same. If you try to map, to take a radio map and an optical map, they don't match exactly. Optical wisp and X-ray wisp are not the same. If you take an X-ray image and you look how the wisp behave, and an optical image and you look how the wisp behave, the optical wisp is not on top of the X-ray wisp. So somehow there is a displacement. And if you think that wisps are only due to Doppler boosting, you might wonder why there is a displacement. I mean, if this is just brighter because it moves toward me, why do I care if it's from X-ray to optical? It should be the same. So why is that optical? It's in a different position than X-ray. And we have tried to model this by associating different acceleration prescription at different position of the nebula. There are lots of indications that acceleration is not uniform at the shock, and that different mechanisms might be placed in different location of the shock. Different particle distribution could be accelerated in different location of the shock. Now, this is easy to do in Crab because it's well resolved and beautiful, and doing that in other systems is not as easy. But there might be evidence also in other systems. For example, Vela, we see nothing in optical in Vela, absolutely nothing. And instead, we have a beautiful bright tori in X-ray. And there are other systems where we see radio that anticorrelates with X-ray, for example. So
yes, good. Okay, it's quite complicated. I mean, but it looks like this needs quite a lot of. I mean, you have gone quite a lot of way. But also, there is another thing about very small. You talked about positrons leaving at the last part of your talk, leaving the pulsars and not producing radio. Why you don't? You said that the interstellar magnetic field is very low. Still, if the positrons are of gamma fiber, you should have a radio emission.
These are very high Lorentz factor electrons. So typically, the Lorentz factor is of order of 10 to the 7, the one that escaped. So those in the 3 microgauss of the ISM, they would emit mostly in optical, which of course is completely foreground dominated and is not visible. You might get, perhaps there has been a suggestion by Barkov and Lutikov that some of the filament that you see in the galactic center region, there are these long filaments that are seen in the galactic center perpendicular to the galactic plane, might actually be high energy particle injected locally by pulsar. So there might be pulsar moving in the galactic center. You don't see the pulsar because it's highly dispersed or it's too weak, but you do see this particle escaping. So it's hard to know, but if one were to manage to find a pulsar sitting at the edge of one of these filaments, it will be a smoking gun telling that probably these filaments that you see in the galactic center are indeed of pulsar origins. And those are seen in radio because there the magnetic field might be a bit higher, or the injection properties might be a bit different.
Okay, thank you. My regards to Reno. I hope he made this many years ago. But
Yeah, there is in Florence there is a long tradition working on Pulsar Wind Nebulae that dates back to Franco Pacini. So,
okay,
I know.
I see another question by Marcus Polkas. He wrote in the chat. I was wondering, maybe I didn't understand, the rise of asymmetry of particle outflow, positive and negative, occurring at the lower energy regime.
Ah, okay. Why? The reason is, okay, I don't have a slide. Let me wait. Okay, let's see. I have to go back. So, why, for example, on these regimes, you have lots of particles streaming in this direction and not much in this other? So the reason is that essentially you escape this where on the side where you have the largest amount of turbulence. So if you look back at the model that I'm showing here, let's see if I have a zoom of the central region of one of these models. Okay, if you look here, for example, you do see that essentially on one side, you have this what's called as a magnetic wall. So you have magnetic field from the ISM, have the same polarity of the magnetic field of the pulsar wind. So they pile up in the same direction, and essentially there is no reconnection at all. There is no current sheet or reconnection going on. On the other side, you have reconnection. This is something similar happened, for example, in the Earth-solar wind interaction. There is one side of the Earth where the magnetic field is reconnecting with the solar wind, and another side where it is not. And this gives different behaviors in terms of, for example, aurora on the North Pole and at the South Pole. You don't have them simultaneously. So what happens is that on one side, you have different polarities. So it's the side where you can have reconnection. So you will most likely escape from this side. Now, by toying with the relative inclination of the magnetic axis of the pulsar in the magnetic field, you essentially create systems where when particles escape, they escape only on one side of the nebula and they stream outward. And this is the reason why you get the asymmetries in the escape flow. There is about a factor 10 difference between the number of particles on these sides and on this other, which is just related to the specific geometry. So you might have object where you don't have, you have two features, an object where you have just one. Unfortunately, we only see two objects where we have these long features for the moment. So, and they're both quite asymmetric, but not completely. I mean, you see some emission coming from the other. The other issue that's important is that you need to confine this particle. So it's not just that you need to have them escape. You need to have enough particle to drive turbulence and create this confinement. So, and this is a kind of a threshold behavior. So if you have, if on this side you have 10 times more particles, they're not just going to be 10 times brighter. They might be 100 times brighter because they might drive more turbulence and get stuck there. On the other side, you have few particles. They will emit less, but they also stream at a much larger distance because they cannot drive turbulence. And so you won't see them simply because the surface brightness is too small. So it's a combination of both things. It's not clear how it works because this is one of the things that we hope to analyze in the future is to understand how to relate these emission properties, these escape properties to the emission of the features. And it's not so easy because this is another regime. It's a free streaming regime. So probably would like to have to use peak codes or something like much more complex environment. But the key idea is that it's a combination of geometry and reconnection that somehow managed to select to one side.
For the first factor related to the asymmetry of the magnetic field, don't you need similar magnitudes of magnetic field inside and outside in order to this to be prominent, to create some real asymmetry? Do you have similar magnetic fields inside and outside?
So the problem is that you end up having it. Because the properties of this magnetopause is that at the magnetopause, you need to have, you reach equipartition. This is the typical properties of magnetopause is that you reach pressure equipartition and magnetic equipartition at the magnetopause. So what happens is that no matter what the magnetic field that you have, close to the magnetopause, you will tend to have a magnetic field of similar strength and of equipartition veils. So in reality, what we have done is quite simple. So if the magnetic field in the pulsar is very weak, the magnetopause is going to be very thin. So there is a problem that you are not going to be able to confine almost anything because the Larmor radii will be very large for almost all particles. So you need a pulsar which is strongly magnetized, but it's not an issue. There are plenty of evidence that the pulsar wind can be close to equipartition. Remember that these objects are much smaller than PWN. So if you take even one of these dissipative wind model, these are about an order of magnitude smaller than PWN, so dissipation in the wind might not be efficient in this system. Because PWN are much larger, so you have much more time to dissipate the strike current, the striked wind or the wind. Here it's 10 to the 16, a few 10 to the 15 centimeters, so you really have to push a lot in order to dissipate the magnetic field in the wind in such a short distance. For the ISM, you have problems that the magnetic field in the ISM is very weak, but in general, what you get is that it managed to reach close to equipartition, or values of the order of 10 to 20 microgauss at equipartition. And these are not very different from the values that you reach inside at the end. So, because these pulsars are moving at about 100 kilometers per second. So, if you look the equipartition pressure at 100 kilometers per second with an ISM of 1 particle per cubic centimeter is about 10 to 20 microgauss. So you don't need that strong compression. So ultimately you are in the right regimes. I mean, you can toy a bit, you can have a bit more diffusion or not. I'm not saying that it will work for all systems and it's a guarantee stuff, but it's not impossible. The order of magnitude for the are typical of the ISM.
Mm-hmm. Okay.
I also have a question, if there is some time.
Yeah, of course, Maria.
Okay, so I have one question related to this part of your talk, where you described a connection taking place in the interface on the one hemisphere. And I was wondering, what prescription do you use for the energy of the particles that get through this reconnection site? So
okay, so the point is that I simply inject I have tried different energies of the particle. So this is a plot with different Lorentz factor of the particle that are injected. And essentially there is a transition regime. If your particle has very high Lorentz factor, they will have Larmor radii that are so big that will essentially diffuse out. So 10 to the 8 is almost the pulsar voltage. So these are really the most extreme particle you can inject in this system.
Okay,
but if you go to low energy particle, they get stuck into the current sheet and they stream out. There is a limit of whether to the energy I can simulate because I have a numerical resolution in my simulation. So I cannot model particles that have Larmor radii smaller than, let's say, 1 or 2 zones, because simply my simulation is not accurate at that level. And there will be turbulent magnetic field unresolved, and I will get the wrong dynamics at very small energy. So I do see a convergence. There are very few particles escaping because only the one that reach this reconnection site managed to get out. But I cannot really trust my advection scheme at a very low energy. I won't trust it.
The reconnection site doesn't play any role at an extra energization of the particles.
It doesn't. So I can follow that. It does not really change things a lot. So the energy gain of the particle, because it's MHD ultimately. So being an MHD site, the assumption is that you have plenty of low energy particles that manage to shield any residual electric field. There is only the induction field, which means that there is only a weak field left over.
Okay, so you cannot.
So it's a reconnection in the sense that somehow if you are gyrating on a magnetic field line, which originally came from the pulsar, you can jump on a magnetic field line which connect to the ISM.
I see, okay.
But it's not a reconnection site where you do have a strong unscreened electric field.
Okay.
Because in MHD simulation, that is not there, essentially. I will have to place it by hand somehow.
Okay. And the other question was related to the first part of your talk, where you mentioned something about the year-long time scale of variability in the pulsar wind, and you gave an explanation with some instability, which I don't remember now the name.
It's the shock instabilities, essentially.
Yes.
So it's something that's asking.
Yes, and the question was, I didn't quite understand how the year-long time scale comes from this stability. Why it is year long and it is not month long?
So the reason why it's year long or not month long, it's essentially based on this problem. So what you are doing here, you are driving vorticity because the shock is oblique. So post-shock flow, if you compute vorticity at the shock, is non-zero. This is a common properties of oblique shock. Vorticity means that downstream you will create eddies and vortexes, and these will drive sound waves. So what happens is that there are two kinds of sound waves. The one that goes outward and they're lost. But there are sound waves that moves inward because the nebula is subsonic. And they will essentially surf along the shock. So you will have the sound wave that surf along the shock. The shock will be perturbed, and this perturbation will feed on itself. So you will modulate the shock, drive the waves, send the waves back, which will remodulate the shock, and so on and so forth. So what drives the characteristic time scale is the sound crossing time of the shock. So if you take the shock, which is about a third of a light year, and the sound speed, which is about c-third, you will get, that's c over square root of 3, you will get essentially the typical time scale is of the order of 1-2 years. Now, this is the problem in PWN, is that no matter what you do, the time scale is always the size of the nebula divided c. So it's very difficult in PWN to understand what instability or what mode you are triggering, because usually in classical system, you can understand if it's an ion mode, it's a MHD mode, it's a sound waves, it's a fast magnetosonic wave, because they have different velocities. And so the size of the system divided by different velocity will give you different times. In relativistic systems, everything moves at c, or a fraction of c. And so you take the size of the nebula, you divide by c-third or by c, and you cannot tell me if it's it's a sound wave, or it's a fast magnetosonic wave, is an entropy perturbation. It's really, really hard. So most of it is based on guess, by looking at simulation and looking at things. But it's really complicated to pinpoint an instability and be sure that it's the proper and correct eigenmodes that get triggered with the correct time scale. You can do this in a box, but in these systems, it's going to be a mess. There are too many things playing together. So ultimately, it's the same problem of ions. There are these models that invoke variability due to ions, and due to the gyration time scale of ion. And guess what the gyration time scale of ions is in a nebula, which is about a few light years long, is a few years. So you go back to that. So ultimately, you always end up hitting the same problems. So you really have to look at the simulation and see these waves, the sound waves that propagates, and you see the sound waves that go through, and the shock that get bended. So you need to analyze the systems. And this is an hypothesis. I'm not saying it's going to be the correct explanations, but at least this is what it looks like when you look at the simulation.
Yes, thank you.
Mm-hmm. I have a very general question. How the resolution of the simulations affect the results that you showed us?
Okay, so for the 2D run, for the two-axis symmetric run, we are pretty confident that the resolution is decently under control. So we have done simulation by, over the year, the resolution has increased by a factor 8. And the result is that the global feature have been preserved. Shock of the bright torus, the wisp features, the global scale of the variability, they all seems to have converged. For 3D run, it's a major issue because the resolution is small and you can't do otherwise you can't be able to do the run. So the 3D simulation had a resolution that's worse than what we were doing 20 years ago in 2D, just to tell you. And if you look at how they evolve, as I say, we are not simulating real plasma, we are simulating honey. It has the same numerical viscosity of a jar of honey, ultimately. So it's tricky, and this is a major limitation. So in 2D, we are pretty confident that the resolution is there. In 3D, there are issues. The fact that 3D is not that different from 2D in the internal region suggests that perhaps it might be that terrible, at least for the X-ray. But for the radio, surely it is, because we can have I say we can resolve mode which is of the order of the size of the nebula. And instead in radio, we see the polarization on scale that are much, much smaller. I mean, if you take a radio map of the Crab, you will see very, very fine structure at the very edge.
Mm-hmm.
So this is one issue. Unfortunately, I don't see that getting solved in the forthcoming future, because you have to imagine that increasing the resolution by a factor 2 in a 3D run means increasing the computational time by a factor 16. Which means that if it takes 1 million CPU hours to run in one simulation, and no one will give you 16 million CPU hours. I can try to ask a supercomputer center in Italy, but they will tell me no. I already know the answer. Perhaps GPU is the future.
Okay, I think it's time to stop even the question session. Thank you very much, Niccolò.
Thank you
for
again. Inviting me.
It was a pleasure to hear you. Very nice talk. So,
yes. And to all of you, we are also having a colloquium next week, despite the fact that it is Tuesday, November 17th, like a national celebration. Next day, we are still having a colloquium.
Okay. Bye-bye to everybody.
Bye.
Bye, and thank you again.
Bye.
Caritas and Maria.
Thank you. Ευχαριστούμε.